range hopping, so effectively it's just a zero-dimensional problem. And what we found, the reason for looking at it is that it gives us a solvable model of a new type of state of matter, which we haven't really had solvable examples of very much. And these are states of matter which have, okay, there we go, that have no quasi-particle decomposition, that you couldn't think of the low energy states as some set of single particle states with some interactions between them. And closely connected to this, but by no means proven, but in all the known examples we know that when this is not true, this also seems to be true, that a positive property of such systems is that when you perturb them, they equilibrate very fast, and they're, in some sense, the fastest possible equilibrations in any system, and the time is basically this universal time just determined by Planck's constant and the absolute temperature. I'm sure you all know Kb is a fake constant. It's just a question of unit of temperature, which really should be energy, then Kb disappears. Okay, so now what I want to do today is take this very artificial looking model and show you in several people in recent work and also not so recent work. I've used it as a starting point for actual experiments in condensed matter. But before I jump to that, I just want to say a few words about black holes, just so that I complete the story and explain why people in other fields are also very interested in this model. So I just try to give you a qualitative picture. So what black holes, of course, you know what black holes are. And when Hawking applied the quantum mechanics to black holes, they came up with two very important conclusions. One is that all black holes have an entropy. And today we can think of that somewhat like an entanglement entropy of the entanglement from the inside of a black hole to the outside of a black hole. So since if you're sitting outside, the inside of the black hole is forever gone, you can never communicate with the inside, you may as well trace over the inside, and what's left over is what you see as a black hole entropy. Similar to the kind of Rindler horizon that Shinsei mentioned. So this entropy turns out, just like entanglement entropy, to be proportional to the area of a black hole. So that's the one very surprising thing. It's a system with entropy is proportional to the area. And then Hawking's brilliant result was that he actually got a number for the entropy, which turns out to be area times Newton's constant divided by 4 in appropriate units, and also a value for the temperature, associated temperature of a black hole was just given by these expressions in terms of Newton's constant, the mass of the black hole, and the velocity of light. Okay. So jumping ahead to recent observations of black holes, I'm sure you've all seen these amazing signals from LIGO of the merger of a black hole. What I want to focus on is the very last bit of this merger, where the black hole after very quickly settles down to be a perfect sphere sitting forever as a sphere. So now in Einstein's equations, which describe perfectly this merger, purely classically, if you solve Einstein's equations, in fact, it settles down to a sphere, and it's just a featureless sphere for all future time. And Einstein's equation also determine what's called the ring down time, the decay time for the merger of these black holes, this very last bit, which is it's kind of an exponential decay of what's called the quasi-normal modes of the black hole, which is nearly spherical. And that time has also been worked out, and it turns out to be this. It's a purely classical time, and it doesn't involve h bar. It's just 8 pi gm over c cubed. And for this 60 solar mass black hole, it's about 8 milliseconds. Okay. But however, there's a new interpretation of a black hole as not a purely classical object, but as a quantum system in thermal equilibrium. That's what Hawking taught us. Every black hole is sitting in thermal equilibrium. So you can think of this decay at the very end as also some quantum system that's coming back into thermal equilibrium. Okay, so in that language, how long does this thermal equilibration take? Well, one of the amazing facts is that if you take this Hawking result for the Hawking temperature and you compare it to this ring down time of classical GR, And they are just very simply related by this very simple relation that, in fact, if you think of it as a quantum system, black holes are quantum systems that equilibrate in the fastest possible time that we know of any quantum system, which is h bar over kT. So it's the same time. And that's fundamentally the reason why you need systems without quasi-particles to be dual, if you wish, to a black hole. Okay, so that's really the most important thing I just wanted to get across. And that's the physical idea between how systems of this type without quasi-particles can realize in some dual representation sometimes black hole physics, because they satisfy one of the preconditions. You've got to have basically any black hole in any geometry seems to equilibrate in this time. I'm not an expert, but that's what black hole people tell me. Okay, so then let me just conclude this stating the result that I've worked out all these interesting properties of the SYK model, the density of states, the entropy, the power law Green's function, this conformal structure of the Green's function, which we then related to SL2R invariance. And this property, I just didn't show you the calculation, but there's various evidence that the equilibration time is also h bar over kT. And it turns out, so these are properties of a zero-dimensional quantum system, 0 plus 1 dimension. And all of these properties, including quantitative terms, can be reproduced as the low energy limit of a certain theory of gravity. And that theory of gravity lives in one space and one time dimension, so that's the holographic principle. And it has to be a theory of gravity where the background geometry is what's called anti-de Sitter space, ADS2. And the reason it has to be this is because this is the same geometry as I indicated last time, which had this.
Sweepers, there will be a meeting at 2:15 at Shelby's Corner.
Okay. So you have the SL2R invariance that picks out ADS2. And there are many black holes that, in fact, okay, this says, who cares about 1 plus 1 dimension space-time? Well, if you take even an ordinary black hole and you get very close to it, then locally the physics of a black hole essentially factorizes. You have one radial direction into the black hole and you have time, and you can, to a very good approximation, much of the physics you can write in terms of just the S wave component of the transverse directions and one radial direction and time. So the low energy physics of many black holes can be written effectively as a 1 plus 1 dimensional theory. But the usual Schwarzschild black holes don't have an ADS2 geometry, but there are charged black holes and extremal black holes, or black holes in globally anti-de Sitter space that do have this geometry. So it's not going to apply to any experiment yet, but it's still a pretty good realization and a pretty practicable realization of the quantum fluctuations near a black hole horizon. Okay, that's really what I wanted to say on this. Yeah.
Does this mean that the residual entropy is a generic feature of all non?
No. So in terms of black holes, so the residual entropy is a generic feature of black holes with ADS2 geometry. So Schwarzschild black holes do not have a residual entropy, at least in anti-de Sitter space. It's a little bit difficult if you take black holes in Minkowski space, they are not in equilibrium, they're evaporating. So, specific heat is actually negative. But if you take black holes in anti-de Sitter space, globally anti-de Sitter space, then they have a positive entropy which vanishes as temperature goes to 0. Right. So, but it's believed that there's a whole class of fairly stable black holes which do have a finite entropy as temperature goes to 0, but those are finite objects. So in some sense, and of course here we are treating it in some infinite range approximation where everything is connected to everything. Whether this, my guess is that this is not a stable thing, that S0 is non-zero for with finite range interactions, but it's not as crazy as I first thought. It's a fairly robust thing. Okay.
You know what's confusing? Me,
Yes, yes.
many people, you can say this is unstable. It will be unstable to Fermi liquid.
Yeah.
And now, can it be unstable to something that's still not made of quasi-particles?
Well, so I'll give you two models if you just hold on, where one model it is unstable, the other model it isn't, so you'll see. Okay, so this is just tying up some loose ends from last time. Also, I just want to mention very briefly, because this is the connection to quantum chaos. I haven't discussed this at all, but this has, of course, also been the subject of much discussion. So there was a very important paper by Schenker and Stanford, which introduced or reintroduced in modern terms what people call the Lyapunov time, which roughly speaking is time over which a many-body system loses memory of its initial state. And they related this to some out-of-time autocorrelation function, which now there's a infinite number of papers evaluating such things. But more importantly, they did two additional things. One, with Maldacena, they proved a lower bound on this time. So this time is, if you wish, is a time that's related to this equilibration time, which is a more physical thing that you can easily measure in an experiment. This is much, much harder to measure in an experiment, but it's easier to compute theoretically, and it's also easier for which you can prove certain things. And this is one of the proofs that this time is always longer than h bar over kt with precisely this factor of 1 over 2 pi. And then they also showed that, first of all, any black hole in Einstein gravity saturates this lower bound. So it's the fastest possible chaos. And Kitev and others showed that the SYK model also saturates the lower bound. So that's another connection between black holes and the SYK model. Okay. Right. So I think that's all I want to say about. This is the end of my first talk. Any questions? All right. Yes, please.
So, I mean, in experiment and telegraphically, there are models that have scattering rates dominated by electric or a magnetic field that's greater than the temperature. Does that somehow violate that bound?
The magnetic field, what?
Yeah, I mean, like magneto resistance measurements can be dominated in a high field regime.
Yeah.
Does that violate this bound?
No, no. I mean, so you can't, so that you're not directly measuring tau L, that's the short answer, for example. But even the equilibration time is not very simply directly related to transport times. I mean, it's hard to, what one can't do for sure is in a system without quasi-particles, take some resistance, put it in the Drude formula n e squared tau over m and get the time. That's definitely not valid. So one has to figure out, it's a much harder task to get a time out of a transport measurement. It's a little easier, say, if you did photo emission or something, then you're directly measuring frequencies, or you're doing some AC conductivity, then you can get time out. But just from DC transport, that's always a dangerous thing. Okay, so my second talk. Okay, so this is the official title, so that's what I'm going to talk about. So now I'm going to really try to talk about some real-world things. So here's my favorite real-world phase diagram of the high-temperature superconductors. And I want to focus on at least a model of this strange metal that's found above the critical temperature. I won't say anything about superconductivity or pseudogap or any such thing. And it's just very crude models. And this kind of strange metal is found basically in every known high TC superconductor in 2 dimensions for sure, and maybe even in higher dimensions with slightly different power laws, with a resistance proportional to temperature. So this particular metal has many pejorative names: strange, bad, incoherent, all mean slightly different things. So strange because, well, the resistance going linear temperature is strange. It's bad because the resistance in some cases is much bigger in 2D, than h over e squared. Now, if you take the usual quasi-particle theory of transport, then we know that once the resistance becomes bigger than h over e squared, then there must be localization. Due to disorder, the resistance becomes so large. So if you take a good metal like gold or copper and you make it's really dirty and the resistance becomes of order h over e squared, then it'll become an insulator around. But here it shows no sign of becoming insulating in the sense that even though the resistance is large, it's an increasing function of temperature. So in an insulator, when you increase the temperature, the resistance is a decreasing function of temperature because you get more excitations across the gap and the resistance goes down as you increase the temperature. So it's metallic in the sense that d rho dt is positive, but it's in a regime where the resistance can be quite large. So that's the bad metal behavior, and again, extremely surprising. And incoherent generally refers to the fact that there's no quasi-particles. Okay, so this is the strange metal or the bad metal problem, which has been around for 20 plus years, maybe even longer. And there is, one kind of simple model that can give you at least resistivity linear function of temperature. That's a model where, say, you have electron-phonon scattering, but all the phonons are very low energy, much smaller than the temperature. Then the density of phonons by the Bose function will be proportional to temperature, and you just scatter off them, and that gives you resistance proportional to temperature. It's as if you're scattering with impurities made up of the phonons whose density is just proportional to temperature. But when you look more carefully, that kind of model never really works because you never see any crossover near the Debye temperature. If you put in more carefully, as Ehresberg and Kivelson have been doing lately, maybe Kivelson will say something about this tomorrow, more carefully the effects of non-offsite couplings, there's always a saturation. So these kind of classical density models don't really work. And today I'm going to present a quantum model, but which still is quantum is very important, but in the end it also has some incoherent or classical features to it. It's really quantum critical. So another important experiments I should say, there was the work of Ian Hayes et al. This is Jim Analytis in the pnictides. And what's shown here is the magnetic field dependence of the resistance. And what they find at high fields is that above the superconducting temperature, so you ignore these downturns, the resistance increases linearly with field. There's divided by temperature to make these curves all collapse onto each other. Here's a more recent experiment from Schechter and Greg Bobinger's on it on the high TC on the list on lanthanum strontium copper oxide. Again, some linear dependence on field, but they plotted it slightly differently. And there are some differences which I'm not fully clear on, which maybe Greg will clarify in a minute. But let me just summarize. So there's a lot of complicated data, but Analytis et al. Claim that if you look at this difference, the resistances in the regimes that they can measure, the HT minus 0, 0, it's basic at H equals 0, that's just linearly proportional to temperature. And at T equals 0 is linearly proportional to H. And to a very good approximation, in between it goes the square root of T squared plus H squared. So that's the very remarkable observation. And as far as I know, there's no theory for this. There's no theory that really has any way. And we've tried for many years to get with the theory with this, and now we have a proposal. So I put it that way. But Greg, if you want to comment on the differences between the two sets of experiments.
So in a sentence, the clear observation from both groups is that there's a linear magnetoresistance.
Yes, yeah.
We find that by going to somewhat higher fields, that we get into a regime where we have rho of T going linear in temperature at high fields.
Yeah.
And rho of H is going linear in field in the same regime.
This is where T is much bigger than H, or H becomes bigger than T?
It's where H is high enough to suppress the superconductivity, so higher than 50 Tesla, going up to about 90, which is the size we can measure. T below about 50 Kelvin or so.
Okay.
So if 1 Tesla equals 1 Kelvin, yes, H is higher than T.
Okay.
But the striking thing is that that quadrature formula
Yes.
cannot apply to that regime.
Yeah, well, okay.
You clearly see linearity in both H and T when we get to high enough fields.
Okay. All right, well, thanks.
Yep.
All right, so let me, before I get to a model that works, or at least, let me tell you about many years of failed efforts in very quickly, so you don't have to do it. So my students' pain, actually. So the typical model, well, there's many, many models, but one class of models that several of us have been working on is a quantum critical point without disorder. So you imagine you have some metal with some Fermi surface, and then you couple it to some low energy boson. So in this case, I just show you the coupling to some gauge field. So in this case, this would be an emergent gauge field because of some topological order nearby and so on. It doesn't matter where it came from. You have some gauge fields coupled to a Fermi surface. So this kind of problem, goes back to probably earliest applications of spin liquids and then also the new half-field Landau level. So in the low energy limit, you can actually show that all the interesting singularities are associated with just focusing in on 2 antipodal points on the Fermi surface and then focusing on the fermions near this point. Okay, so these fermions then couple to the gauge field, and you can write down some continuum action and try to study its properties. And a very large number of papers have done that, and I won't bore you with all the details. But the basic understanding is that there are 2 things that happen. First is because there's a Fermi surface, the Fermi surface damps out the gauge boson. So the gauge boson has a self-energy, which goes as, in this case, omega over q. So this is Landau damping of the gauge boson. Then you put this Landau damped gauge boson and compute this one diagram. And in 2D, you get this omega to the 2/3 self-energy. So this is, even to this day, it's probably the best understood and most reliable example we have of a non-Fermi liquid state of a system without disorder and finite in 2 dimensions. So this is omega to the 2/3, and that's much bigger than omega, and so it's a non-Fermi liquid, and there are no quasi-particles. Remember, in the SYK model, you had square root of omega, which is also which is even a bit larger. But here, in addition to the self-energy, you also have the dispersion. So there's a momentum dispersion, and then omega to the 2/3. All right, so this seems that you've got quasi-particles getting scattered a lot. There's a lot of damping, and so surely there should be a lot of resistance. And many papers have computed using some kind of Boltzmann theory where you just apply Fermi's golden rule to these incipient quasi-particles which never actually exist. And you apply Fermi's golden rule, and you compute some resistivity. And you may have heard about T to the 4/3 and other strange power laws from that approach. Okay, so I'm here to tell you that that answer is simply not right. I'm not here, people know that. And the reason is very simple. It's an analog of the effect which is called Phonon Drag. So there's a very interesting controversy going back to the very early days of quantum mechanics. Bloch wrote his first paper on electron-phonon problem and predicted that the resistivity due to the electron-phonon interactions in a crystal should be T to the power 5th. That's Bloch's law. So hopefully you've all seen that in your Ashcroft and Mermin textbook. And that's been observed, so everyone's happy. But that was in 1931, I think. And then 1932, Peierls wrote 2 papers saying Bloch is completely wrong. That can't possibly be right. And what he pointed out was that if you have electrons scattering off low energy, long wavelength phonons, the electrons transfer some momentum to the phonons. But eventually, the phonons will give that momentum back to the electron. So if you set up a current, another way to say it, if you set up a current, that current carrying state has some momentum. And that momentum will not decay. It's always preserved. So there will be some net current that will always keep flowing. So the resistance should be 0. This is what Poyles pointed out, that Bloch's calculation is not right. If the resistance is 0, it can't possibly work. But Bloch's calculation works. We see it in experiment. So what's the problem? Well, the problem is this is in some ideal world of a crystal that has no impurities. So what happens in practice is that the electrons give the momentum to the phonons, but the phonons lose it to the impurities. So that momentum never comes back. So once an electron scatters off a phonon, you can forget about that phonon. And the electrons have indeed lost the momentum, and so Bloch's calculation works. So impurities save the, so two things save the day. One is there are always impurities, and two is that the electron-phonon coupling is weak. It's a small correction. So here the problem is the electron-photon coupling is not weak. In fact, it's infinitely strong. It's so strong that the quasi-particles don't even exist. Where did it go? Yeah. The electron-photon coupling is so strong that it destroys the quasi-particles. So the strongest thing in the problem, even if you have weak density of impurities, is the electron-photon coupling. So it's not even valid to think of the electrons and photons as separate objects. They're really together in some quantum critical fluid, and they're carrying the momentum together. So this whole system has a conserved momentum, and eventually that momentum may see some impurities, but because the electron-photon coupling is infinitely strong, the momentum is never lost. So in this theory as written, the resistance is exactly 0. And we should be listening to Poyles and not Bloch for this problem. So you can make this all formal. There is a conserved momentum in this theory, and the resistance is 0, even though the quasi-particle lifetime is so short. So this goes back to the question of whether you simply cannot convert resistance to resistance is actually 0 here. So how do you get into resistance? Well, you have to put in Umklapp or something like that. So you put in some small corrections due to Umklapp, and these end up giving you a small resistance. And it's on all the cases we looked, well, there are some cases with impurities with linear resistance, but it's still a relatively small correction to a background, and is not the primary process that's giving you the damping of the quasi-particles, or the destruction of the quasi-particles. So anyway, so this indicates to me that it's going to be almost impossible to find an explanation. I don't know of any of the linear resistivity problem, let alone the linear magnetoresistance problem, in a theory without disorder. So we have to really take into account seriously the effects of disorder. So there's been, of course, a huge amount of work on the effects of disordered interactions in electron gas. This was in the 80s when people studied Anderson transition and localization and interaction corrections to the Anderson transition. And what they found was that there were some regimes, at least in 3D, or in some cases even in 2D, where the metal was stable, and where the interactions were weak, and you got a metal with quasi-particles. Or you found some flow to some strong coupling in with disorder, where you assume that you became an insulator. But perhaps there's some other fixed point at strong interactions and strong disorder where the quasi-particles break down. And because the quasi-particle break down, localization effects also disappear. And you get a metallic state, a conducting bad metal state, which is present somewhere in the regime of strong interactions and disorder. And we'd like to understand that. OK. So with that propaganda, let me just give you then some toy models of this possible fixed point of disordered metals. OK, that's, of course, the SYK models. All right, so I'm going to talk about this model a little bit. This appeared in a paper by Song, Jian, and Balance. And actually, pretty much this model with the same properties, but in a more confusing way, already was present in Georges and Parcolet in '99. But this is much nicer to think about and see. So what the model is you take this SYK dot that I talked about yesterday, and you just make a lattice of it. So within each dot, think of each dot as some multi-orbital atom. So there's n orbitals on this atom, and there's some general interaction term for the n orbitals on that atom. And we just take these interactions to be random. And in this particular model, they take the interactions to be different random numbers on each atom. You could also take them to be the same numbers on each atom. But there's some set of numbers. So this is some nucleus with some numbers. You just take the same nucleus everywhere, or the same atom everywhere. I won't describe that. There's a paper, I think, coming out this week by Debanjan, Senthil, Eresberg on that model. It has closely related properties. And then you take some hopping between these atoms. And in this case, the simpler model is that these are just random numbers. So if you may remember, yesterday I talked about the random matrix problem, which is single particle hopping, and then the two-particle SYK model. This is some kind of interpolation between them. So within each dot, it's the SYK interactions, and between the dots, it's the random matrix term. Okay. And basically, then you send n to infinity, and this turns out to be a model that's exactly solvable. So in the limit n goes to infinity in any dimension, this is a solvable model with strong disorder in interactions. That already makes it quite interesting because we don't have too many of those. Okay. And as I said, that you can also actually relax the disorder. You can make the UIJKL the same on every atom. And you can make the T also completely regular. And it's just a little bit more complicated, but it still works. Okay.
So is n the number of dots, or n is the
No, there's an infinite number of dots. N is the number of orbitals on each dot. It's not a zero-dimensional model anymore. Okay. But if you take at least the leading large n saddle point equations, and you can do them exactly the same way I discussed last time. You just draw all the graphs and you average over the UIJKL and the TIJ. And the answer turns out to be very simple. It's just the sum of the two terms that I had last time. So yesterday I had these equations for the SYK model. So that's the self-energy of the electrons, and the self-energy was cube of the Green's function. That's the SYK equations. And then for the random matrix model, I had this equation, where G inverse was proportional to G. So if you solve this equation, you get the semicircular density of states, which is a Fermi liquid. Okay? So now you just add them. So this model, it turns out you get both contributions, and everything is independent of momentum. So even though this is a d-dimensional model, at least the single electron Green's functions are independent of momentum. But because it's living in d dimensions, you can compute things like diffusion constant, transport, and they did that, and I'll talk about it in a minute. Okay, so hopefully you can all see where this came from. It's just the sum of the two things I wrote down last time.
Do you think of this as a mean field theory of sorts or not?
Yes, it's a mean field theory. If you want to call it a dynamical mean field theory, I'll go along with that. But it's in finite dimensions, and it's slightly different, but it's in the, so now you have to solve for G and sigma, and you can do it. So what the short answer is, what happens is that if you go to low enough frequencies, then this term is always more important than that one, because this term is linear in G and that's cubic in G. This is more important. So you throw this out, and then you just have a quadratic equation which gives you a Fermi liquid behavior. So as you said, you recover Fermi liquid behavior at low enough energies. So one question is, how low in energy is that? So the first guess would be at least, there's a matrix element, hopping matrix element T here. So once your temperature is smaller than the hopping, it should be a Fermi liquid. That's what you would naively guess. So the naive guess turns out to be wrong. If you solve these equations, you'll find that the energy scale is not T, but it's T squared over U. So it can be very small when U becomes very large. And one way you see this is you just take these set of equations and rescale everything. So you define a new Green's function with a factor of t out front, and you rescale both your frequencies and your times with this energy EC, which is defined over here. And you plug this all in, and you get a new set of equations. So these equations then become these equations. And in these equations, there's no parameters except the t over u over here. But this I omega, however, doesn't matter at low frequencies. So you can throw this out. And now it's parameter free. So that you can just solve it. There's one universal set of equations, and the natural scale for everything is EC. So t squared over u is the scale where you cross over from non-Fermi liquid behavior to Fermi liquid behavior. So, so they've actually solved this numerically. I'm just showing you results from their paper. I believe the paper is now published in PRL. So if you look at the electron spectral function, it has a 1 over square root of omega. In the pure SYK model, it diverges as omega goes to 0. Here it saturates at the energy scale, which is EC. Okay. Then I got many questions about the entropy. So yes, the entropy is what was a 0 temperature entropy dives down very rapidly, again, at a temperature of order EC. And this means that the gamma value, which is the slope over here, is given by the 0 temperature entropy of the SYK model divided by EC. And since EC is so small, this can be very large. So there's a large mass enhancement. So that's the very large gamma value with a linear specific heat. Okay. And finally, the most interesting thing, now you can do some transport. So they've done very carefully the full calculation. But here, let's ask what is the conductivity at temperatures bigger than EC. So in here, the Green's function in this regime should be just the SYK Green's functions, okay, with the 1 over square root of omega. Now this is the basic formula in fact, this is exact in this theory, but you can think of this as a perturbation in T naught, or it's exact in the large n limit. This is just the Kubo formula for the conductivity, where A of omega is the electron spectral function. And now, so this thing, however, now if you did this, for electron scattering of phonons, to get a linear resistivity, you need the spectral density of phonons to be essentially delta function at temperatures at frequencies smaller than temperature. Here, on the other hand, the natural scale of everything is T. Everything has a scale of omega over T. So you're looking at fluctuations where h bar omega is of order kT, not much smaller than kT. And then so this turns out to be 1 over temperature. And now why is that? Well, that relies crucially on the fact that A of omega is 1 over square root of omega. So this is 1 power of omega here, 1 power of omega here, 1 over square root of omega here, 1 over square root of omega here. You're left with 1 over omega, and that's the 1 over T. So the fact that it's a linear resistance is not something that had to work out. It works out, it relies crucially on the square root exponent and the quantum criticality of the SYK model. It's really very much dependent on the structure of the SYK model, this U term.
The semi-concept is really there.
It is, yes. Yes, it is, pretty much. So now here they can compute the resistance at all temperatures. And so what they find is that the resistivity at temperature bigger than EC is of order H over E. So it's a bad metal. It's T over EC, and T is bigger than EC. So I can say it's a bad metal. And at very low temperatures down here, it is T squared with, again, some prefactor that's determined by 1 over EC. So there's also a Kawadawi-Woods ratio having to the ratio of this A term here and the specific heat, and that's also universal. So the Kawadawi-Woods ratio also works out in the regime of small AC. All right, so that's the model of Song et al. And and also quite similar in many ways to a much older model of George and Parcolet. Okay, but this model, it's a little more pleasing to look at. You could imagine in some dream, while you're dreaming, that maybe there's an actual cuprates which looks like that, but all right, fine. It's some large orbital limit, okay. Any questions on this model? Yes?
Is there a Fermi surface for this particular surface?
So that's not really, no. This is an incoherent metal, and it's just 1 over square root of omega. Self-energy dominates everything. If you made the Tij non-random, then there will be some remnant of the Fermi. So the model I've shown you, the simplest model, is one in which the Tij are random numbers. Then there's no sign of a Fermi surface. You can also study a model where the Tij are not random. Then there's at least a ghost of a Fermi surface. That paper is not out yet. I think it should be out this week, my friends at MIT tell me. Oh, thank you. Right, right. So that has some data on that, right? It has a remnant Fermi surface, right? Yeah, okay. Right, but in any case, the broadening will be much larger than the temperature, than the frequency.
Here's an important question that was emphasized by McCarthy and Mackenzie. They said that when you cross the Mott limit,
Yeah.
then through the peak in the optical conductivity totally disappears.
Yes.
The optical conductivity no longer rises above that. So can you remind us what happens here?
I don't know. Again, there's certainly no Drude peak. I wouldn't call it a Drude peak, but I suspect there is some peak, I suspect.
Yeah, well, so they say that peak, may not be the Drude form.
Yeah.
It could be some other form, some other power law, but there is something going up at low frequency.
Yeah.
Whereas above the Mott limit, they say generically, this is gone.
Yeah. I don't know what the answer is. There might be computations in this paper or the George Parcolet paper, I don't remember. But whatever, there might be a little peak, but it's definitely not a Drude peak. It's some kind of quantum critical peak in optical conductivity. Okay, so that's a nice model, but the trouble with it is it cannot explain, as we'll see, the magnetoresistance data. In fact, what I'm going to talk about now is Avishkar's work. There's a poster by him over there, and I'm going to give some of the background to that poster. And in fact, this was the first thing I told Avishkar, look at this model and compute the magnetoresistance. He told me it didn't work. Okay. So we had to look for other models. And he found something that worked, and that's what I'm going to talk about now. It's a variant of this, it's slightly different. And this was a paper with John McGreevy and Dan Arovas, which just appeared at the end of December on the archive. Okay. So the model, let me just tell you what the model is, and then we can worry about why this. It's a two-band model. So we just use SYK and make a Kondo lattice out of it. So here are the same SYK atoms, multi-orbital atoms here. And now previously I had electrons hopping between these atoms. But now I assume that the electrons here are basically trapped. They're just sitting in these regions, and they're behaving like little SYK sites. There's n of these in each of these. And then there are mobile electrons drawn with the green. You have to make a better picture, but anyway. So the greens are electrons that are hopping without any disorder. So the green is the C electrons. They're hopping without any disorder. The Fs are the SYK electrons here with some random, now we're calling them J couplings. And then there's a Kondo exchange, if you wish, which you're calling G, between the mobile electrons and the SYK electron. So that's the model. And in this case, we take GIJKL and JIJKL to be random, take n electrons on every one of these dots, and this is solvable, exactly solvable in the large n limit. Okay, so some other kind of mean field theory where of a Kondo-like lattice, but where the spins are not just single spins, the spins are SYK regions. Okay? So this model, it looks ridiculous. No, it isn't actually. well, the first thing is that this thing can fit all of the data. Yes. You had an objection, Kun. So is it clear what the model is? So let's just view as as Avishkar says, we're just engineering a model to fit the data. And then we worry about, is this reasonable model or not? Even that's progress because no one else has engineered any other model that works, as far as I know. Okay. All right, so you can take the large N limit, and you get a different, slightly more complicated set of equations, but very similar to the SYK equations. So for the F electrons, you had sigma is G cubed. This is what I spent so much time on yesterday, the sigma equals G cubed. And now you get one more contribution, which is from the Kondo exchange with 2 contributions from the conduction electrons here. And then for the conduction electron, you have a self-energy, which is, again, this type of graph. So it's basically, again, the melon graphs. But since there's 2 types of electrons, there's 2 types of contributions. So for the SYK electrons, which I'll draw them in pink, there's these graphs, which we had yesterday. And then you also have the conduction electron, which I'll draw in black, which is this sort of interaction. And these are the conduction electrons, and these are the F electrons. And then for the conduction electron, you have the scatter of the Fs. So you get this graph. That's it. You just put these things together. Everything turns out to be independent of momentum. And you get these equations that you have to solve numerically, and you can actually make a lot of progress analytically. So I showed you all the techniques and how you do these things yesterday. It's more of that. On the scale of what people do in dynamical mean field theory, this is a totally baby problem. People do much more complicated solutions in dynamical mean field theory. This can, I don't know, it takes a few minutes on your laptop, right? Okay. So what do you get? So I'm going to focus on this regime where the Kondo exchange is large. So then as a function of temperature, you get 2 different regimes. And we're going to call them incoherent metal and marginal Fermi liquid. So in the incoherent metal, this is the high temperature phase, it's like everything is SYK. So everything has a 1/square root of time behavior with slightly different prefactors. We've also worried here about the particle-hole asymmetry, but just ignore all of that. You remember this from last time. This was the Georges Parcolet guess for the Green's function. And this works for everything. Basically, all the Green's functions, the coupling is so strong that everything here becomes 1/square root of time. Okay. On the other hand, if you go to lower temperatures, then you get a slightly different behavior. Then in this regime, the marginal Fermi liquid regime, the conduction electrons, the SYK electrons, this dominates, and you just get 1/square root of omega. But if you take the conduction electron, then you get physics which is very close to the original paper of Varma et al. You have some conduction electron scattering of a bath of these SYK electron, and this bath has precisely the marginal susceptibility. So that's because this thing, this particular contribution is d omega gg of the F electrons. Each of this is 1/square root of omega, so this becomes log of omega, roughly speaking. So the calculation here is very, the same as the calculation in the first marginal Fermi liquid paper, and indeed you get the omega log omega in this electron self-energy. All right, so that's what this model does. You can compute the resistance or the conductivity using the Kubo formula. And you find it's linear resistance in both cases, in both temperature regimes, over here and over here, but with somewhat different coefficients. So you can imagine there would be, in this model, 2 different regimes of linear resistivity with slightly different slopes, which is also not ridiculous given some of the things that are seen. Okay. Now, however, to get the magnetoresistance, we have to be in the marginal Fermi liquid regime. We have to be in the lower temperature regime, where your resistance is quite a bit smaller than h/e². It's only there that we find linear magnetoresistance. When you go to higher, when everything is local, the magnetic field essentially has no effect. All right, so the magnetotransport, so this is, from this point on, I would really refer you to Avishkar's poster. When do I have to finish? I'm over time anyway, right? So Avishkar can tell you much more about this. So you just take, essentially put a Lorentz force due to the magnetic field. And it doesn't average to 0 because there is a non-random hopping. You need some non-random hopping for the conduction electrons. And then you have a collision term which has this marginal Fermi liquid form, from which you can compute the longitudinal and the Hall conductivities. And they all end up scaling as B over T. So in other words, they cross over from B dominated to T dominated by a scale that's very close to the type of scale that Analytis et al. Talked about. However, this is not sufficient to get you a linear magnetoresistance. If you take these sigmas and put them into the resistance, the magnetoresistance, you still get a B squared magnetoresistance as you would get in basically any model, any kind of Boltzmann model. So to get a linear magnetoresistance, we had to refer to much older work of transport in systems with mesoscopic disorder. So here you take, so we've talked about this lattice of SYK dots coupled to conduction electrons. And now we assume that that entire system we talked about before is inside one of these circles. Okay? And then there's some more macroscopic inhomogeneities. So as far as we're concerned, everything we talked about before was a way to compute the longitudinal and transverse response to one of these circles. So now we're just going to solve Ohm's law. So we have some sigma of x, which we just determined, which was this sigma of x that comes from quantum mechanics, which has both a longitudinal and transverse term. And then we're just going to solve Kirchhoff's equations. So when you solve these equations in the presence of disorder, this is what was done by many people, going back to Dickney, I think. This is some numerical work of Parrish and Littlewood. So what's being shown here, the color is the voltage and the arrows are the current. So you apply there's a magnetic field and you're just solving for, this is the high school problem of solving for Kirchhoff's laws with some transverse terms. You put a voltage here, and you look for how the current flows. And what you find is due to the Lorentz force and the inhomogeneity, the current seems to take this rather convoluted path. And the length of this path increases linearly with field, and that's kind of why you get the linear magnetoresistance. So there's been many papers on this. Peter Littlewood has several papers. There's an effective medium approximation that Avishkar worked out that you can read about here. In some simple limits, we do get the T squared plus B squared behavior, but one could imagine other things coming out from different distributions of disorder. All right, I went through that quickly. Well, all right. So this is the conclusion of this part. So there's a simple solvable model which just consists of lots of islands of these SYK dots which scatter conduction electrons. And ridiculous as the model may seem, it gives you all the observed features. It gives you as a function of field and temperature. And it tells you, and it also has some constraints. That model is not totally free. This kind of behavior only appears not in the bad metal regime. It appears in the marginal Fermi liquid regime, but the resistance is smaller than h over e squared. It requires disorder. We don't see how you could possibly get the linear magnetoresistance in a perfectly clean sample. Okay. So that's the model. Okay. And I'm very happy about it, given how many years we've thought about these questions. But I think it's a good starting point for where we want to go from here. So maybe I'll say a few more things. So let me just speculate, and then I'll stop. Where does this, why is this model at all reasonable? So, okay, maybe in the cuprates where you have 5 orbitals, and 5 is infinity, well, maybe this is okay. But in the pnictides, In the cuprates, you have one orbital. Oh, okay, some people say you have two. That's not infinity. So, and there's only one orbital near the Fermi surface. So it's really a one-band model. So why should a one-band model look like this Kondo lattice model in the presence of disorder? So the question is you know, going back to the introduction of my second talk, is there some general theory of strong interactions and disorder that will end up giving you a theory, a fixed point of which we have this mean field theory? This is, of course, only a mean field theory, but it already has a lot of structure in it. So can we start from a single band Hubbard model disorder and end up with a two-band fixed point? Well, so at this point, I just want to mention actually my earliest papers in my career as a postdoc at Bell Labs, where I also was, this was before high TC came on the scene, if you can remember something that ancient. Well, you were not alive, many of you, I suspect. So before high TC became all the rage, people were working on something called phosphorus-doped silicon. And there were a lot of experiments on it. And they were interested in the metal-insulated transition in phosphorus-doped silicon. And here's a toy model of phosphorus-doped silicon. These are the phosphorus nuclei, the dark circles. And each phosphorus nucleus atom has one extra electron. Okay, so that electron has a Bohr radius about 100 A naught. So it's a very big atom. So we're talking of very low energy scales. And so that electron is trapped around this nucleus. And then the electrons can tunnel from one side to the other. So it's like a Hubbard model. So that's, you know, I was working on Hubbard models before high TC came on the scene, where the hopping matrix elements are random. So the general picture was, if these impurities are very dense, then the overlap was so strong that you will get a metal. When the impurities are very rare, you will get an insulator, because that would be the Mott-Hubbard transition. And there was this huge amount of work on this, which was all abandoned the moment high TC appeared. But some of the experiments showed some rather interesting things. Actually, 92. Yeah, I think there was well before our theory work, there was some other experiment. Anyway, this is one of the things I found. So you can try to measure the spin susceptibility. So now if you're on an insulator, imagine these are really far apart. So there's one electron sitting on every, and it'll just have it's a free spin. It'll give you a Curie susceptibility. So you'd expect the spin susceptibility to diverge as temperature goes to 0. But when there's strong overlap, you get a metal and should have a Pauli susceptibility. So you'd expected a transition in the spin susceptibility right across the metal insulator transition. So people are measuring transport, and they see, you know, metal to insulator behavior, but then they measure the spin susceptibility, and here's 3 different tracks of the spin susceptibility at different densities. And this is actually on 2 sides of the transition, and you can't tell where the transition is. So it seems as if the system, as far as the spins are concerned, looks almost insulating. This is almost a 1/T behavior. Then there's some also very, very nice work that Kun Yang was also involved in figuring out why this is not 1/T, but some other powers of T and all of that. But it looks pretty much like it's an insulator when you measure the spin susceptibility. You measure the transport, it looks like a metal. So there's this dual character to this material, even though it's a single band Hubbard model. Here it definitely is a single band Hubbard model. So what's the origin of this? And this was one of my first, actually probably my first PRL or something. No, second PRL. I don't know. So this, and actually Milovanovic was my student before Jinwu. So what we argued was that even in the presence of weak disorder, the system had this tendency to kind of separate. There'd be some sites, like this site, for example, which would look insulating, and other sites would look conducting. And we gave various reasons why that might be natural. Anyway, so my hope is that perhaps something like this is also happening here in the cuprates, where not something simple as this, where you get single spin, but just because of the local disorder, some regions are becoming SYK-like, other regions are insulating, are conducting, And so you've got this the system that can have both then linear magnetoresistance and linear resistivity in temperature. Anyway, so that's the picture. It's the best picture I've seen so far, and but maybe it's all wrong. We'll see. It has many constraints. I mean, disorder is really crucial to it, clearly. And I guess I'll just stop there.
Time for a few more questions.
So another important aspect of this strange metal
Yeah.
is that when you look at the Hall angle,
Yes.
it actually behaves all the way as t squared.
Well, it depends on who measures it to some extent, I think.
Has that been checked in?
Yeah, I'll let Avishkar answer that. Yeah. You want to say something, Avishkar? The Hall angle.
If you put in various kinds of disorder realization, you will get different Hall angles in the spin metal. Yeah. You're using this technique.
I think all experimental groups would agree that if you use magnetic fields that are powerful enough to start suppressing DC,
Yes.
that the measured Call coefficient comes off of the 1 over T. It either saturates or in fact decreases. So that regime in which that behavior has been reported is a high temperature regime.
So the Ong-Anderson behavior is 1 over T squared, right?
Yes.
Yeah.
Cotangent of the Hall angle.
That's right. Yeah, omega c tau, basically. Yeah, so I think,
Well, the voltage is still linear. The IVR relationship is still linear.
But the Hall conductivity is no longer linear.
Linear in what?
In magnetic.
No, it still is.
It's still is?
Yes.
okay, so maybe if I can rephrase what Avishkar said. So our theory had two parts to it. One was the marginal Fermi liquid theory of the SYK dots. And that very robustly gives you these type of behaviors for the longitudinal and the Hall conductivities. They both scale as 1 over temperature times some function of B over T. Here it's B over T squared because you pulled out one factor of B over T. So this is a robust and constrained part of our theory. Now we can combine this with global mesoscopic disorder of various types. And there's some freedom in what kind of Hall angles we get from that. That's something we need to study a little more carefully, but it's not as tightly constrained. Yeah. So the global inhomogeneity seems to play an important role in what the temperature dependent on the Hall angle is in this theory.
Questions?
Yeah.
Yeah.
So there is a statement that was made by Henry Mackenzie. He was giving a number of talks on what you may call bad metals.
Yeah.
And asked, can you make in one sentence a statement, what are the materials where you see this? And he said, these are all systems close to the multi-dwelling state.
Okay. Fine.
Based on the known.
Yeah. All right.
What's your view, because this, what you describe here is more like a heavy fermion problem, and it's not necessarily tied down to integer filling or to
No.
mod physics. So how
Well, no. I mean, to get the SYK dots, there is some mod physics there for sure. Yeah, well, I would say that I don't disagree. It's connected to mod physics. Yeah, that's mod physics is a very broad term. I mean, we're trying to be a little more specific than that. But it's yeah, you're right. The model in the end is more like a heavy fermion model, but the very last part of my talk, I tried to motivate why even from a Hubbard model, Mott-like Hubbard model, you could get the same physics.
Well, the point was that, are you close to an insulating state? Because
Well,
insulating is okay.
well, you have doped away from it, so okay. But but you're right. In general, I'm just thinking about I think the way I like to phrase it, I'm just thinking about new classes of fixed points of systems with strong disordered interactions. Whether it's actually near a Mott insulator or not, I mean, I think that's open to, you could probably get in a variety of situations. I mean, that's another thing I like about this model. It's, it's kind of general and simple because the behavior is so ubiquitous and so universal. That's the kind of explanations you want. You'd have some particular theory with the SU2 gauge fields and with a certain type of Fermi surface. It's not very general. This is, very simple and general. Lots of randomness.
Did you use, I already forgot your
Yeah.
Separate, so are the two fermions, right, so you can separate between the chemical potential.
Yeah, it doesn't matter what the chemical potential. Well, the way there's Mott physics, if you wish, is that there's some emergent conservation law. Each of these regions conserves the number of electrons. No electron hops out of this region. So there's some emergent local conservation laws. So that's sort of in the spirit of, emergent gauge fields or something. So there's definitely some Mott physics in that sense, that the number of electrons in each of these regions is conserved. We're not, in a Kondo model, you're conserving at every site. Here we're kind of relaxing that a little bit.
So regarding the single band Hubbard model,
Yeah.
in 2007 there's a paper by Nandini using mean field.
Yes.
The one orbital Hubbard model.
Yeah.
Random disorder on site.
Yes.
And precisely with the interaction, she was able to show there is a metallic phase.
This was in the negative U Hubbard model, wasn't it?
Positive repulsive U Hubbard model.
Okay.
And in 2017, I extended that to finite temperature,
Okay.
precisely showing the non-Fermi liquid behavior in finite temperature.
Okay. What was the origin of the non-Fermi liquid behavior?
We still couldn't get to it because it's a mean field model. I did Monte Carlo simulations.
Okay.
If it has quantum critical origin, then we cannot.
So it was you did quantum Monte Carlo on a Hubbard model at finite doping with disorder.
This was ad hoc filling, classical Monte Carlo, but we benchmarked this against the quantum Monte Carlo data to make sure that our simulation is correct.
Classic. So you're combining some Hartree-Fock treatment of the interactions with
With Monte Carlo.
with the Monte Carlo was on the anti-ferromagnetic order.
Right.
Yeah.
Near half filling, as he was mentioning, close to the Mach phase.
Yeah.
With disorder.
Well, okay.
Precisely
Yeah. I mean, that sounds very interesting, but I think it's somewhat different physics than I'm discussing here. Yeah.
Another thing is for hoop rings.
Yeah.
This seems quite large amount of disorder. And we working on that kind of disorder. Experimentalists cannot do such a bad job at making.
Well, well, I mean, the long scale disorder for, you see it in STM. I mean, you see in any sample they've looked at. Okay, they haven't looked at YBCO, but I suspect there is also. So I'm not so worried about the long scale disorder. The short scale disorder here, this is kind of what I was trying to argue over here. So one of the things we found, and this is one of the points of this paper that I wrote a long, long time ago. In this paper, what we found was that even relatively weak disorder was sufficient to give you regions where you had localized spins. So it was enhanced by the interactions, for sure. And the disorder was so weak that all the one electron states were extended. Everything in the Fermi level was completely extended, nowhere near Mott localization. But nevertheless, there was local inhomogeneity that was enhanced, and you get local spin fluctuations in some regions. This is also consistent with these experiments here. I mean, this is the densities, twice the density of the Mott transition, and still you're getting free spin behavior. So these are also fairly, these are beautiful silicon crystals, of course, but okay, on the scale you're looking at, they are somewhat disordered. Yeah. But fair enough, and I will also point to then this upcoming paper by, let's see, well, I know three of the other, Debanjan Chaudhary, Eresberg, and Senthil, which is about to come out in next week, which has very much similar physics. It won't have the linear magnetoresistance that I needed for global scale disorder, But up to this point, I think they get very similar results. I haven't seen the paper. But up to this point, they get this same behavior in a model without disorder. But lots of umklapp. But yeah, okay.
Do we have to think of disorder as imperfections in the crystals, or can nanoscale phase separation and maybe even fluctuations in phase boundaries?
Yeah, well, I think, sure. I mean, so like I've just emphasized, there's two different scales we need disorder. One, at least one scale is, this fact that the system splits into Kondo regions and non-Kondo regions, or SYK region, non. So that's very microscopic. And I was arguing that may not even be necessary. There may well be that even in a non-random model you can get that physics. And then there's the large scale disorder, which we need not to get the linear resistivity, but to get the linear magnetoresistance. And there it's not a new model. This has been around for a long time. And here, yes, the kind of things you're talking about would probably, the nanoscale inhomogeneity would contribute here.
Okay, so I guess maybe it's time to thank Subir again.